Hi everybody, this is Dr. Pingle. This is part 2 of the Spatial Interpolation series, Producing Smooth Grids.
So last time we looked at one method, a couple of different tools to produce what we call 2D histograms, but they're all in a class of point to raster conversions. The one that we used was actually point to raster, which is what you see at the right. And to do that, we looked at point data for crime statistics in Chicago for the month of October 2016. So the map that you see at the left is all of those different point locations mapped out. And as we said, it's difficult to get a sense of the overall pattern because points can kind of exist one on top of another, and so it can be difficult to tell what's a densely clustered section and what's not. So when we run tools like point to raster, we get something like we see at the right there. This does a good job of aggregating, but what it doesn't do is really smooth things out a little bit. So you tend to get this very blocky appearance. That's not necessarily a bad thing. If you're doing exploratory data analysis, it can be helpful to sort of get a reasonably good raw look at the data. But most of the time, if you're going to be presenting these things for publication or for presentation, you're going to want to smooth those out a little bit. So to do that, we're going to look at two different techniques. One is a kernel density estimation technique, or KDE for short, and the other one is point density. So the point to raster is essentially a 2D histogram, and histograms work by binning the data. So we would count how many phenomena occur in this cell, how many occur in that cell. And this is sort of an example of what that looks like from statistics. The histogram is in the top left pane, and we just count how many different observations fall in each bin. What we want to do is we want to smooth that out a little bit, and so we're going to be moving towards things like the kernel density techniques that you're seeing there at the bottom. And these are just sort of moving averages. They get a little bit more complicated than that, but that's not a bad way to think of it at the beginning. Histograms themselves are ways to sort of look at the distribution of data, and so there are many different ways to do this, but a really good way to do it is to visualize things via sort of an idealized curve. So we would fit a curve to the data, and we would sort of look at that curve to see what we think that the underlying distribution looks like. So one way to take a look at this is to look at the empirical distribution. So what we're really trying to do here is to not make assumptions about what kind of distribution underlies what we're interested in, but rather sort of model the data as it exists. Oftentimes that's going to create a phenomenon of what's called overfitting. So we're not going to get the sort of smooth, idealized curve that we might if we just sort of made a guess about what the underlying distribution is. But the nice thing is that we don't, by not making those assumptions, hopefully we don't get misled by those assumptions either. KDE techniques require what's called a kernel, so this is where the K comes from, to do that smoothing. So again, you can kind of think of this as sort of a moving average. We're going to use the observations that are around us to help us get a better sense of what our pixel or our bin should be. But to do that, we need to decide how we're going to weight or count nearby observations. So the simplest way to count nearby observations is to have what's called a top hat kernel. And this is just a straight sort of moving average. So you just count how many are within a certain radius. And if it's within that radius, it gets counted fully. If it's outside that radius, it doesn't get counted at all. But there are more sophisticated kernels. So there's Gaussian kernels that are essentially like a normal distribution. And there are a number of different versions of this. But essentially what we're doing is we're weighting observations such that nearby observations get weighted more, distant observations get weighted less, and there's sort of a continuous fall off rather than this steep one that you see with the top hat. And I like to think of these things as paintbrushes. So if you've ever played around in Photoshop or anything like that, you can define the kind of paintbrush that you're using, and the kernels that you're seeing here are a lot like that. It's really a shape or a brush, and that's going to determine how nearby observations are weighted. The two tools that we're going to be talking about here today are kernel density and point density. There's a line density that'll work on line input features if you're interested in that. And both of these are found in the Spatial Analyst extension. But again, most of the time I just would search for these. So point density tools are going to create a raster, just like the point to raster tool that we looked at in the previous lecture. But instead of making a 2D histogram with very rigid boundaries, we're going to make a much smoother image. And we're going to do that by using the simple 2D kernel, like the top hat kernel, so that nearby observations, if they're within a certain radius, they'll get counted. If they're outside that radius, they won't get counted. So you're either in or you're out. You can also specify a population field. So if, for instance, each point may have more than one observation associated with it. So if you were out on safari and you recorded a latitude and longitude position of 3 zebras versus 1 zebra, if you had a population field that's associated with that latitude and longitude, you can use that to weight the observation. The neighborhood itself is going to define the kernel. So there are a number of different shapes you can use. Most of the time you're likely to use a circle, but you can do things like define sort of like a donut shape or an annulus. So you might have an inner and outer radius. You can define rectangles, wedges, so plenty of different options. Most of the time you're likely to just use a circle, but it's nice to know that other things are available. So you're essentially going to define a radius for that circle. You can either do it in terms of pixels, which is often common, or you can use map units. So you would say within 100 meters or within a kilometer, things like that. So essentially what you're doing is a kind of a buffering operation. You're just counting how many observations fall within a certain radius of a given pixel, and you're giving that pixel that value. So you're essentially applying a buffer on every single pixel inside the raster. So this will smooth things out. It'll start to give you a better sense of clustering. But there is a good chance of what are called artifacts in the image. So an artifact is sort of the way, sort of a leftover based on either the data or how it was processed, leading to some misleading results. In this case, this is Husky bus tracker data, so point values for the buses running around the area near Northern Illinois University. There are a lot of points that overlap, but you can see that when buses are stopped, you wind up with these sort of odd circle shapes. And these are the artifacts that I'm talking about. This is a result of using that point density tool that counts you as either being in or out. One way around that is to use the kernel density tool. So essentially this is the same kind of thing. It's a moving average. We're counting the number of things within a certain radius. But the difference here is that we're diminishing the value of what we count with distance. So instead of just being in or out, we weight things according to the distance they are from my pixel cell. So essentially this is just a difference in the weighting scheme. Instead of counting all at once, we've got this sort of gradual drop off. And you can see this if you zoom in on the image or the two images. You can see that point densities form this large single value circle, whereas the kernel density is going to drop off gradually. So instead of all of the pixels within a certain radius having the same value, they decrease with distance. Most of the time, if you want to do these calculations, you're probably going to want to use kernel density, although you should be aware that kernel density is more difficult for the computer to calculate. So this is going to tend to result in longer calculation times. If you're only calculating, tens of thousands of points, it probably doesn't make much difference. But if you're calculating millions of points, it might. So you'll want to take that into account when you're choosing which tool to use, point density or kernel density. Both of these, by the way, are related to wider topics within geography. So gravity models and distance decay are both ways of expressing the idea that the influence or the connection between 2 points drops off as a function of the square of the distance. This is an example of the point density applied to crime statistics for Chicago. So this is quite a bit smoother than the 2D histogram. We've got, it does a pretty good job of sort of taking all of those point data and looking for the clusters or the very dense spots. So it's quite a bit smoother than the 2D histogram, and it makes much more sense than the point data. For this one, I used a radius of 1,000 meters, 1 kilometer, of a circular neighborhood. The output size is 100 meters. Always be careful to make sure that you've got an appropriate projection defined so that the computer can make sense of these in units that are intelligible. You notice that there's a couple of artifacts that come out of this, though. First of all, in the northwest, you see these big circles. So again, we're using this moving window where you're either in or you're out. So isolated points will show up on this kind of a processing technique as kind of giant circles. And you can see that especially at the edges where things are less dense. The other thing that you'll notice is in the lower right, especially, and at the top, you've got this very odd clipped pattern. This is because you're trying to apply a smoothing technique near the edges of your map. By default, when you use these tools, it's going to work out to the extent of your data. So oftentimes when you're applying these things, you're going to want to expand that data using an environment variable, or expand your processing area using an environment variable. So I wanted to leave it in here because it's a common way to go wrong, and I wanted to draw your attention to that, and I'll show you how to fix that in the applied part of the lecture. This is the same data processed using kernel density techniques. So the tool is very similar, same kind of inputs. You have to define a cell size, and you'll want to define a search radius. These will be supplied automatically for you if you don't want to do that, and most of the time those are pretty reasonable. But I wanted to keep these the same to allow for easier comparisons. In comparison to the point density technique, this is a lot smoother. So you have fewer sort of artifacts. Those giant circles that we saw in the northwest are not present. You do still have those odd clipped borders on the edges, and for exactly the same reason, the processing extent is usually going to be applied only to the bounding box of the point data. So you can have these sort of odd edge effects, which again is fairly easy to fix, and I'll show you how to do that in the applied lecture. This is an example of all three images put together. So the point to raster is what we did in the previous lecture. This is just sort of binning the values and seeing what they fall into. Point density is going to apply a fixed radius to this, and kernel density is going to use a sort of a smoother kernel to smooth this out. So in comparison, both point density and kernel density are much smoother. They both work very well for hotspot analysis. But kernel density is even a bit smoother than the point density. You can see that in comparison, there are a lot of sort of isolated tiny little clusters of pixels in point density. You get these artifacts that you can especially see in the northwest, where you get these very circular shapes. And in comparison, the kernel density are much smoother. On both of those, you're going to see that when you get to the edges of your map, you can get these sort of crisp drop-offs. So in the applied part of the lecture, I'll show you how to fix that. But I wanted to make you aware of that because it's an easy thing to go wrong, and you can fix this fairly easily just by working through the environment variables. So there's your quick look at producing smooth rasters out of pixel data. This is a really handy technique to know. A lot of times your point data is going to be very dense, and you're going to want a way to simplify that and to help your readers see patterns. This especially applies at the local level, but it really could apply at any scale. So hopefully these will be a couple of good tools for you to have in your toolkit. Thanks for listening, and we'll catch you next time.